Using our model system of the ideal gas inside of a piston and the PV diagram, we can now talk about a variety of different processes that we can take this gas through to get from one state to another. We've talked about some of these processes already. In particular, this first one we're going to talk about, which is an isothermal process, we've talked about previously in our example. An isothermal process is a process where the temperature does not change, and that makes sense because iso means same and thermal means temperature. So T is a constant, so T1 equals T2, and that's actually true for any location along the path from state 1 to state 2. We also can see that P1V1 equals P2V2 by the ideal gas law. Putting this together, we can actually find an equation for the pressure as a function of volume, which is equal to nRT, which is just a constant here, divided by the volume, as we said earlier. That can be represented by this line here connecting points 1 and 2. The work done by this system is just equal to the shaded area underneath that, and using some calculus we can find that the work is equal to nRT, the same constant, times the natural log of the final velocity over the initial velocity. We can use the conservation of energy law, which is the first law of thermodynamics, to show, and knowing that the total energy is proportional to the change in temperature, we can see that delta U is actually 0 in this case. And that means that the heat transferred into or out of the system is just equal to the work done by the system. The next process we'll talk about, we also slightly touched on, which is an isobaric process, which means that the pressure is the same throughout the process. This is represented by a horizontal line on the PV diagram. P is constant here, so P1 equals P2 for all locations along that horizontal line. And we can see that using the ideal gas law that NkBT1 over V1 equals NkBT2 over V2 for a process where the pressure is constant. We can find the work done by this system, which is just equal to that constant pressure times the change in volume. Interestingly, the change in volume is directly proportional to the change in temperature. So we can write that the work done is just equal to NkB delta T. Delta Q is, as always, equal to the heat capacity times the change in temperature. And putting this all together into the ideal gas law, we have both a heat term and a work term that must go into it. And using the fact that the change in total internal energy is 3/2 NkB delta T, we can plug all of these different parts into our first law equation, and we get 3/2 NkB delta T is equal to C delta T minus NkB delta T. Interestingly, both the work term and the total internal energy term have the same types of units and look to them. They both have an NkB in them. We can gather them together to find that we can write an expression for the heat capacity at a constant pressure, which is just 5/2 NkBT. So for an ideal gas going through a constant pressure process, you can find that the heat capacity is just 5/2 NkB. This is quite interesting that we have an exact equation that can tell us what the heat capacity is for this system. Another process that we can do is an isochoric process. This is a process where the volume does not change, so V is constant, V1 equals V2. This is represented by a vertical line on our PV diagram. If P is constant, then by the ideal gas law, nRT1 equals P1, and that's divided by P1 is equal to nRT2 divided by P2. Interestingly, because there is no change in volume, that means that the work done is actually equal to 0 for this system. The heat exchange is non-zero because it's just proportional to the change in temperature for this system. And putting all of this into the first law, we actually can reduce it to be of a form that the internal energy is just equal to the heat capacity. Using the fact that we know what the change in internal energy is depending on the change in temperature, and plugging in for delta Q, we can find that the heat capacity for an ideal gas and constant volume is 3/2 NkB. This should strike you as somewhat unusual because we just said that the heat capacity for an ideal gas was 5/2 NkB. And this shows you that even though this is the exact same material, the heat capacity can actually change depending on how the system goes through a thermodynamic process. And in particular, the reason why we have a higher heat capacity for a pressure change for a constant pressure is because some of the heat actually goes into doing work during that process. Whereas during an isochoric process, none of the heat being added to the system is going into doing any work on the system. All of the heat added to the system is just being used to change the total internal energy of the system. The last process that we are talking about is an adiabatic process. This is a process where no heat is transferred to the system. So Q is a constant, so to speak, meaning no heat transfer. Delta Q is 0. We can reduce our total internal energy equation to say that delta U is just equal to the negative of delta W, which is the work done by the system. And then we also know that delta U is still proportional to delta T by 3/2 NKB. Putting this all together and doing a lot of math, we can find that actually that the pressure times the volume raised to a power of gamma is a constant. That means that we can rewrite the pressure as a function of volume, which is just equal to that constant, whatever it may be, divided by volume raised to the gamma power. That, when plotted, looks like the plot to the left here on the PV diagram. It's actually a steeper curve than what you would have for an isothermal process. And in fact, the temperature does change in this process, and there is a change in total internal energy. This gamma, interestingly, is equal to the ratio between Cp over Cv, which ends up being 5/3. The work done by this system can be found by integrating under the curve, and you get this nasty expression. Don't worry, I won't ask you to do it yourself, but you can just use this for any problems where we ask you for the work done by an adiabatic process. Finally, the last type of process we're going to talk about is a cycle. This is a process that can be composed of the other different types of thermodynamic processes, but which the overall initial and final states are the same. So for instance, if we start at P1, V1 here on our PV diagram, which is represented by this red dot, we can move by an isothermal process down to this orange dot, which is at P2, V2. Then we can use an isobaric process to move to P3, V3, and then back up via isochoric process back up to P1, V1. In this case, the initial and final states of the system continue to be at the red dot, P1, V1. So T initial equals T final, P initial equals P final, V initial equals V final, and U initial equals U final. These are all state variables that describe where you're located on the pressure volume plot. So the states are all completely well described by both these variables and the equation of state that we have, which is the ideal gas law. And during the cycle, the heat and the work are being exchanged, but the total internal energy of the system after one cycle is actually equal to 0. And you can see this because the delta T for a one whole cycle is also equal to 0. That means that the change in heat, or the heat exchange, is equal to the work done by the system, and that's given by the amount of area inside this curve, which is shaded in purple. These systems are the basis for engines, heat pumps, and refrigerators, and so understanding how they work will help you to understand how these different systems and machines work. They're all around you in your cars and in your house, and keeping you warm and keeping your food cool.